Okay, so before we start, let me give a brief introduction of our speaker. So first of all, I'd like to thank Sumit for accepting the invitation on such a short notice. I know you are very busy these days. So Sumit Dai, he got his PhD from Nanyang Technological University, Singapore. He has a lot of experience in spiked neural networks and neuromorphic computing. And currently, he's a research scientist at iSquare Singapore. Yeah, that's about him. I think now uh, we can start. So the platform is all yours. Sumit.
Thanks for the introduction, Rakesh. Let me share my slides first. So in this talk, I'll not be going in depth about spiking neural network, but I hope to give a brief overview of the neuromorphic computing technology, and hopefully that will pique your interest in the field and have you guys interested in this topic. All right, shall we proceed? Do you see the slides?
Yeah.
So I guess in the audience, all of you must be familiar with standard neural networks and AI stuff, right?
Yeah, I think should be. We have most of the ML engineers here. Yeah.
Yeah, cool. So I couldn't hear that. Was anybody saying something? Anyway, so let me start with the motivation for artificial neural networks, right? So in artificial neural networks, the basic idea is you have massively parallel but simple computational units, and that is trying to replicate what's happening in a brain, right? So natural brain is the benchmark or an inspiration for an artificial neural network. And how we do that in a standard ANN terms is you have this very simple synaptic interactions in the form of affine transforms, weight multiplication basically, and that's followed by a nonlinear activation function. That's also a simple mathematical function, right? So in neuromorphic computing, we use this extension of ANN, a small niche area of ANN called spiking neural network. So basically, we increase the degree of biological realism one step further. Right? So neuromorphic computing, as the name suggests, is you try and replicate what happens in a real brain in silicon in the form and functionality. So basically, that means we are looking at very sparse communication. Local computing is also important. Local computing meaning that you process the inputs and outputs that is local. In addition, when you try and learn in the systems, you only use the signals that are available locally for a neuron, right? Massively parallel interconnected system, that's where the brain gets its robustness, and you try and mimic that. That's also true for standard neural network, but that's even more true for neuromorphic computing. And we're also looking at paradigm of spatiotemporal interaction. So I think that will be explained in the later slides. And the most important thing is a low energy computation. Let me give some numbers on that. So if you Google what's the power consumption of a human brain, right? So that will come around 20 to 25 watts, right? In comparison, where I guess most of you are used to using GPUs for your computation, right? And if you look at the power consumption of a standard GPU, that's 300 watts, right? And now let's compare about the versatility of the human brain versus what a GPU-based solution is capable of, right? A human brain is very much flexible. It is able to adapt itself to many different tasks, whereas a GPU solution that you get is only fine-tuned for a particular task, and you usually cannot extend it to some other tasks unless you do some form of meta-learning stuff, right? So this is a very beautiful quote from Kaval. He's also known as the father of neuromorphic computing. right? As engineers, we do foolish to ignore the lessons of a billion years of evolution, right? So as I said earlier, a human brain or a natural brain is the benchmark for artificial general intelligence system, right? Sorry, not artificial, a general intelligence system. And with AGI, you're trying to replicate what happens in the brain, and that's kind of a best hope to get similar kind of performance in an artificial system. So that's a brief overview of neuromorphic computing. Usually this topic is rather new. So as I present stuff, there might be lots of new stuff, and I usually often feel that the audience lose track or interest in the talk. So nowadays I usually start with a few examples so that will keep all of you motivated towards the talk. Also, if you guys have any questions, feel free to pop in any questions and we can discuss them. Otherwise, you can write it in the chat and we will address them later. Right? Let me know if the video plays. So this is a classic example of a neuromorphic computing system that uses a spiking neural network. So I'll come to that later. So can you guys see my laser pointer?
Yeah.
Yep. So basically, this is a neuromorphic system in action, and the input is captured using a neuromorphic version of a vision sensor called dynamic vision sensor. That's like a camera, but neuromorphic. And I'll briefly tell you guys the advantages of these neuromorphic systems. And this is what the input looks like. So as you see that the input are, usually the video inputs are always spatial, right? But you'll have more of a temporal correlation along the input. That's why we talk about spatiotemporal correlation in spiking neural network. Think about processing a similar system using a standard neural network. Let's say a video, so you process each frame of the video one by one. Let me replay this again. One by one, so that is you process the pixels and you get a numeric number at the output, and based on that you try and classify, right? That's different in spiking neural networks. So in spiking neural network, you get a binary events in time called spikes. So each of these particle lines are spikes in time, and your x-axis is the time. And you'll see that whatever is the correct class, you get more activities on those spikes, as demonstrated in this bar plot as well. And as it goes along, the network gets more and more confidence along the way, and that's how you basically do classification using a spiking neural network. And this actually runs on a neuromorphic hardware as well. So this is another example. This here basically this black plot, right? Black bar is the input of a DVS camera basically, and what you're seeing is an intensity, but it's very noisy, right? And using basically the idea of dynamic field tracking, so it's the idea of lateral inhibition. What that actually means is whenever a neuron fires, it will try and suppress the neurons that are laterally far away from it and try and activate the neurons that are close to it. That way, what we can do is we can track the object. So this bright object is being tracked on the right plot. So these are a few of the examples. Hopefully, this will keep all of you guys intrigued for the rest of the talk. So now again, back to neuromorphic computing, right? So neuromorphic computing is all about the mimicking the brain in silicon in the form and functionality, right? So in this plot, this x-axis is the time, and let's look at the kind of computing paradigm that we have had, or that were developed along the time, right? Initially, we have CPU-based computing; those are quite popular. You get number crunching and everything, but as you progress along the time, we went away from CPU, that's a single core, serialized computing, to parallel computing using GPUs. And as you went along in time, the applications became more and more intelligent applications rather than simple logical applications, right? And we believe that neuromorphic computing is the next step towards that. In addition to being more and more intelligent, the systems also gradually progress towards being more and more biologically realistic. That's because for a general intelligence system, brain is the benchmark. The best system there is, and you try to mimic whatever happens in the brain in artificial system. So as we progress, we try and develop more and more intelligent applications, and that's where the resemblance to biology increases along the way. So I think I put this word a couple of times, the spikes, right? So what actually is spike? Let me explain that. So this the plot on the bottom. So it's a recording of mice hippocampus. So that's the voltage recording of the neuron in a mice, basically. And what we see that usually the voltage is static, or it's varying, but it mostly at a lower level. And there are few discrete time instances where the voltage increase suddenly by a big margin, right? That's where neuroscientists say that the neuron has spiked. And whenever a neuron spikes, information is transmitted along the synapses. So basically, in a biological system, your currency of information exchange is spikes. So the biological neurons process input as spikes, and it will also process its activity as spikes. So, and these sudden surges in voltage of the neuron is what is called spike or action potentials. So this is a single neuron. If you look at the activity of a population of neurons, so each of this dot is a spike of individual neurons, who your y-axis will represent the neuron ID, whereas your x-axis is the time. And here we can see a bunch of neurons that are synchronizing and producing different activities. So this is basically a spike raster plot. And it is what happens in biology. It's a binary information exchange. It's very sparse. And these are events in time. So usually your spikes are not, they vary in magnitude, but usually they are far away from your resting potential right here. So that's why usually people consider spike as binary events, that you ignore your magnitude, and the time when you spiked is more important. That is what brings the temporal information or temporal paradigm into the mix. And one of the intuition why you could say that biology chooses spikes, it might be interesting that not all of the biological brains in our system use spikes. There are some primitive animals where you don't actually have spike, but they communicate in terms of the real neuron voltage. But as the organisms evolved, spikes was the way of information exchange in a biological system. The reason, one of the intuitive reasons for that is usually spikes are, when a neuron spike, the voltage changes by a big magnitude. That's where it is not going to be affected by an inherently noisy system. So that's how the neurons are able to communicate with a high signal to noise ratio. So with spikes, again, in every system, we need some kind of sensors that needs to produce spikes, right? I showed a few examples for using a dynamic vision camera. So this is the example again. So let me explain this. Here you'll see some blue and red pixels. Let me know if the video is slowing down for you guys. And so you will see red and blue pixels that appear randomly at different points of time. Those are called spiking events that are captured by a dynamic vision camera. And these are captured asynchronously. Asynchronously is the key, because when you think of a standard camera, your frames are being captured at, let's say, 24 frames per second, 240 frames per second. Those are captured in discrete intervals, right? And even this camera is going to work in a different way. So each of the pixel operates asynchronously. That's where what that means is, as soon as the receptor receives enough photons in its bucket, it will spike an event. And that happens asynchronously. That gives us very high temporal fidelity. So this particular signal, you can have a temporal fidelity of few microseconds. Compare that to a standard 24 frames per second camera, and the timing information in your frame is just 42 milliseconds apart, right? That's orders of magnitude plus. But when doing so, you don't spend a lot of energy. That's the key. And since everything is asynchronous, you can have high dynamic range. Basically, what that means is when you point the camera to a sun, you can look at this activity around the sun as well as in dark regions around the sun whenever an object flies or does something in a dark region. You can also see both of them together. That is basically not possible using standard camera. Along with camera, we also have silicon cochlea models where these are the spiking activity of audio signal that's been encoded by a silicon cochlea. So they work very similarly to a human ear. So that's modeled in a real silicon, and that they'll produce spikes in different channels. So you can think of them like small hair receptive cells in a cochlea system. So these are some of the examples of the sensors that people use in this field. That doesn't mean that we cannot use standard data to process using spiking neural networks and use it in neuromorphic hardware. I'll come to that later. But with these neuromorphic sensors, the catch is you already have spikes and you can natively process them using a neuromorphic hardware. Let me know if you have any questions up till now. Otherwise, I'll proceed to some intuitions on spiking neural networks. No? Okay. So in that case, spiking neural network, we're simply saying it's a mathematical model of a biological neuron. So that's the model comes from neuroscience. And as I said, the currency of information exchange is using spikes. What it means is your inputs are also spikes, and your output is also going to be spikes. Right? To compare it with standard ANN systems, you can think of them like activation functions. For example, in your neural network, if you replace a sigmoid or ReLU activation function with a spiking neuron, that's a model of the real biological neuron, then what you end up is a spiking neural network system. And as we saw that spikes are discrete events in time, you inherently build this temporal aspect in the system. Let me figuratively describe what happens in a spiking neural network. So bear with me. Let me know if you have any questions along the way. All right. So this black line is what we call the voltage of or membrane potential of a spiking neuron. So you can think of that as the internal state of your activation neuron. And whenever you have an input, your input comes through a synaptic weight, right? And based on that weight, the input at this particular point of time will elicit a temporal activity, a change in the membrane potential after that time. And usually the response is a kind of alpha function. It actually depends on the neurons as well, but it will elicit temporal activity in the neuron. And similarly, you can also have negative weights that will, instead of increasing the membrane potential, they will decrease the membrane potential. So those are called inhibitory postsynaptic potential. Simply what that means is you decrease the weights. And usually an accumulation of all of the input spikes along with the synaptic weights is the linear accumulation of all these inputs is going to be your membrane potential in the system. So that is very much similar to what happens in a standard neural network, right? So you can think of this as a fine transform, multiplication by weight and addition of bias, right? So it's pretty much similar up to this point, but usually a neuron has has a threshold voltage called usually represented by theta. That's called neuron threshold. So whenever this neuron exceeds this threshold, the membrane potential, so it will also fire an output spike, and that's how neuron responds to all of the inputs. A spike meaning that its voltage is going to drastically increase, followed by a slow inhibitory phase of the neuron, and this is where the neuron has responded to all these 4 different input spikes coming through different synapses with different synaptic strains, and this is where the neuron has responded. As you can see that inputs occur in the history and your neuron is going to spike sometime later, but it is also able to accumulate information, probably not in this one because that was too far away, but it is able to accumulate information of these 3 spike inputs at different points of time. So it is able to accumulate these forms of temporal information and then produce its output. Whereas in a standard neural network, you get the numeric input at once. You calculate the affine transform, you do the nonlinear activation function, you get the output. For the output, you are only processing all the inputs that are in that particular point of time. You don't usually consider temporal informations. So that's where spiking neural network are quite different than an ANN. And this temporal information usually is able to provide some form of short-term memory to the system. What that means is a spiking neural network can process these temporal tasks sometimes better than a LSTM network. You replace the activation function of a standard ANN with a spiking neural network, then what happens is you are able to process continuous stream of input spikes coming in. The neuron respond in terms of spike. So you can process spatiotemporal data and produce output spikes. That is going to happen continuously as long as the inputs are there. Your parallel and locality also comes in connections, the synaptic connections, and your spatiotemporal modality comes from the spikes and the spatial information in the input. So that's basically a simple introduction to spiking neural network. I believe, I'd assume that along with these, the neuromorphic sensors that already produce outputs, sensor outputs in terms of spikes, you guys also should be more interested in how to convert the general numeric data into spikes. So there are different encoding strategies, but this this is still an active area of research, so things are not stable in this field. What usually people do is, I'll quickly go through it. So you can have like a retina, you can have different receptive fields. So receptive field is this Gaussian crops that are separated in the region. And whenever you have the input, different receptive fields are going to have different level of activity. So this particular receptive field has a very low response, whereas this particular receptive field has a very high response, right? And a highly activated receptive field is going to spike much faster right here, whereas a receptive field that is not activated enough is not going to spike, or is going to spike later. So this is one way to encode spikes. The problem is for an input, you're going to have multiple channels of encoding, and sometimes it might not be as effective, especially for videos. What happens in a neuromorphic dynamic vision camera is a simple threshold encoding. What that basically means is your input in log magnitude. So log magnitude is necessary. That's very important. But in log magnitude, whenever your input is increases by a certain amount, you just spike either one spike for increase in value, one spike for decrease in value. So that's where you get true polarity of spikes. So that's how you encode using threshold encoding. The reason why people use log magnitude is because log magnitude actually means change in scale of the information, and that's how you get you can just increase your activity in log magnitude, and that's how you get very high dynamic range in these event-based camera systems. We could have more bio-inspired models that use bunch of filter banks, and currently with newer techniques, we are able to learn this filter bank response end to end. So basically, your temporal signal comes in, you pass it through different filter banks along the way, and you just apply your spike activation loop. So that's this feedback loop, and that's how you get your input spikes encoded from a real signal. Another very common is you randomly generate position spike techniques. I will provide some reading links as well. So I'll put them up in the later slides, but position spike is you spike more, given a pixel intensity, you spike more where if your intensity is quite high, pixel value is quite high, and you spike with less rate when your pixel value is low. As simple as that. So why neuromorphic hardware, right? So we want to do neuromorphic hardware because you want a very energy efficient system. Also, a basic property of neuromorphic hardware is you have integrated memory and computation unit. Your synapse is the memory, and your computational unit is the neuron, and those are always local. And what that also enables is very fine-grained parallelism, right? And why we want to do it in hardware is mostly because of this lucrative energy efficiency. We find that even in this budding stage of research, a neuromorphic hardware is orders of magnitude energy efficient than a conventional deep learning solution with using on-the-edge devices like MoVDS or NVIDIA Jets and things like that. So that's why neuromorphic hardware is very promising for on-the-edge computing, and we have different industry efforts doing that. There are efforts from IBM, that's called True North. Intel is also investing heavily on this neuromorphic hardware system. It's called Intel Loihi. You can look them up. So there are Spinnaker, BrainRub, BrainChip, and many different startups that are trying to leverage this energy efficiency of neuromorphic hardware. And at the heart of all this neuromorphic hardware, the computation engine is what we call spiking neural network. So you can think of a neuromorphic hardware as a processor, whereas a spiking neural network is the operating system, the software that is going to run on a neuromorphic hardware. A couple of more examples. Let me know any questions up to here. Otherwise, I will just demo a couple of different examples.
Hi, I had a question. First of all, thank you. This is like a really cool presentation. Thank you for your time. I had two questions. First one is, you were talking about temporal patterns in the spike, and you were showing a slide of like there was a blue and green and orange,
Tell me when to stop.
Slides back, sorry.
This one?
Yeah, this
yep,
one.
Yep.
Yeah, so I was just curious. So you were saying it's like temporal. So does the order of these, this stimuli also matter? Like, is it only because the blue, the rightmost blue, the light blue neuron is linked to this neuron? Is that the reason it's firing, or is this specific pattern of like?
No, right?
Orange
so it's a combination of all this, because when you let's look at the green, the spike coming through this green synaptic connection, right? So it's influence on the membrane potential is just this one. When your this orange spikes come in through a different synapse, your accumulated membrane potential is somewhere along these lines, right?
Right.
and you have still not crossed the threshold.
Right.
So a slight input at this particular point, although it's a bit too far because you have already crossed the maxima, but after this, it's able to elicit a response that is going to increase in the threshold. So it's a combination of all these three, right? Although you could say that at this point of time, this neuron, the response of this neuron is pretty much negligible. So you could say that this spike coming through this synapse, its response is this up to this level, and an additional step is
I think
provided
to
by this
further clarify my question, what I meant is like, what happens if the green one comes later? Will that matter? It just seems like it's like if it crosses that threshold, it'll spike, right? Like it
Yes,
doesn't
correct.
matter the order of these colors.
It
right?
doesn't matter. Yeah.
Okay.
So as long as synaptic intensity, the weights, right? It's same. Where the spike came also doesn't matter.
Oh, that's cool. Yeah, another quick question is that you were talking about hardware level applications. I was wondering if there's any software things that we can, like kind of just to fool around and see how it goes. Is there some way to try
Okay.
that
So
ourselves at home?
for spiking neural networks, right?
Yes.
There are a couple of training frameworks that you can use to train spiking neural network or encode the inputs into spikes and all. Also, there is this framework called Nengo, Nengo. If you Google it up, you can actually download and install. It's a very interactive environment where using a spiking neural network, you can do a PID controls, or you can train networks, do all sorts of fancy things. They have very good demo as well.
I see. Thank you. Yeah, we'll try it out.
Sure. So, do you have any more questions, or otherwise I'll just proceed to some of the examples that are using neuromorphic hardware or spiking neural networks essentially. So this is I guess all of you must be very familiar with MNIST digit recognition. This is neuromorphic version of MNIST, where an MNIST digit is converted into spikes using a dynamic vision camera that we'll see right here. And as in the DVS example, we'll see the spike registers on the bottom across the time. So yeah, let's see. Yeah. So this MNIST image, it's converted into spikes using DVS camera, and that moves in a saccadic motion. Basically, what that means, it will once go down, then a diagonal up, then go left. So each of them lasts 100 milliseconds long, and as you see that the spiking neural network is responding in 3 different saccas. Maybe this is the first one, different group of activities on the second, and the different group of activities on the third saccade. And the separation is quite clear in comparison to the DVS gesture because of this saccadic movement. And we can see that the spiking neural network learns to respond depending on the saccades, but it always tries to respond with more number of spikes for the correct particular class event. Yeah. So there are also, in addition to this, the dynamic vision sensors and silicon cochlea. There are also skin sensors that are very much popular at the moment. So skin sensor is, you could think of it as a robotic haptic application, or surface softness detection and different kind of stuff to be used in a robot. And the advantage neuromorphic computing and neuromorphic sensing adds here is, since the sensor is going to produce its output in terms of spikes, you don't need to have very high bandwidth communication from the sensor to a processor. So that's a very real advantage. There are different forms of skin researches. Let me see if this video, please. So this is one of the skin sensors that was developed in National University of Singapore. So the sensor is on the tip of the fingers, so you can actually put it on a globe and use it to sense different kind of surfaces. Okay, right here we see the person pressing on the finger, and it's responding with spikes based on the pressure at different points. And you can use this to categorize text. You can use it as a feedback to the robotic system to say if the surface is hard or soft, and the robotic hand is going to respond depending on the texture of the surface. Right. So those are possible. Let me stop this video for now. But you could look up this stuff, say, online as well. I cannot see the slides. Yep. Also, there are even more bio-inspired approaches using spiking networks. So this one was from Intel recently, where they model olfactory system in the brain, and using a similar model in a neuromorphic hardware, they were able to classify different odors. And what they were able to do in terms of a standard deep learning benchmark, they were able to do it almost 1,000 times faster and more efficient, energy efficiently than a standard deep learning solution. So that could be one of the examples, but these are taking the spiking neural network paradigm even more bio-inspired by copying the connections that exist in a real biological system. So let me see. So this camera, right? This is what an event-based camera looks like. It's like a standard camera, and what's amazing is this camera is able to capture information at microseconds resolution. A microsecond resolution is 1,000,000 frames per second. Imagine a standard frame-based camera that captures data at 1,000,000 frames per second. You need a very big hard drive with a very big cooling system, and you'll be able to capture only less than a few seconds of information using that. Whereas this tiny unit is able to capture all this information, and it's not going to be very big as well, meaning that you can store all the information in a small SD card. So what's happening is this camera is looking at this pencil, and what it's trying to do is it's trying to balance it vertically, and this is possible with a simple feedback loop because of the very high temporal fidelity of this sensor. So since the sensor is able to respond very fast, it's able to detect where the pencil is falling down, and it is able to quickly respond and balance the pencil. So that's a simple neuromorphic system in place. There are different versions of this, but this one probably doesn't use a spiking neural network. It's just straight away input from the camera, and since the information is you have very low latency, you don't need any further processing on top of that. This is a different example where we have this foosball. You can see my pointer, right?
Yeah. So
we have this foosball field, and it is trying to track the ball in the foosball field right here in this video. So you'll see the circle that's tracking the ball, and the thicker circle is the temporal filtered, Kalman filtered estimate of that block. So you're trying to track the football. The basic goal is you'll have humans playing on one side and this neuromorphic system playing on the other side, and you're going to have a foosball match. It's kind of a World Cup, a robot World Cup kind of scenario for neuromorphic computing. Those are the few examples. I will email these reading stuffs as well, but these are the few resources you could look at if you are more interested in this topic. In today's talk, I didn't go into much technical details about spiking neural networks. I just wanted to give a very brief overview of neuromorphic computing and what's possible with it. there are also other applications like you can actually do path search, or you can also do optimization, like you can solve a Sudoku using a neuromorphic hardware. There are different alternative possibilities, computational possibilities using neuromorphic computing, but spiking neural network and general intelligence is one of the major goals, and you want to do that with very low energy resources for on-the-edge computing applications. So that's what neuromorphic computing is. Yep, thank you.
Yeah, thank you, Sumit Dai, for a cool presentation. So I think we can do QAs now, right? So first of all, I'll ask you some questions. The first question is, can we see your face? Because I think everybody would love to see the face
Oh,
of
okay.
today's speaker, right?
So then I'll stop sharing.
So when necessary, I think you can just show the slides.
Yep, that's
Yeah,
me.
hi, yeah. So everybody knows. Okay, now. So that was a cool presentation. So does anybody have any questions? I think you should have a lot of questions, right? Because it's a new thing for
I
most of
hope
us.
so, unless people
Yeah,
are not interested.
yeah.
How much? How different is it in terms of the data it requires? How different is it than a normal neural network? Does it require more data or less data?
No, you mean the spiking neural network, or?
Yes, spiking neural
So
networks.
spiking neural network, since you're communicating with this sparse events, right?
Mm-hmm.
So your information exchange is going to be very slow compared to a standard neural network. So that
I see.
there are different ways of training a spiking neural network. One of the common strategies is you train a standard ANN and you convert it into a spiking neural network. So there are different
Mm-hmm.
conversion mechanisms. Those with those, still you're going to get gains in terms of amount of data flow, or also that also translates positively in terms of the energy consumption.
Mm-hmm.
But what you find is, if you train a spiking neural network directly rather than converting from an ANN to SNN,
Mm-hmm.
you can train much more efficient and much more sparse communicating spiking
I
neural
see.
networks. Also, let me add, since these spikes are going to be appearing at different points of time, right?
Mm-hmm.
The computational advantage is you don't have to do this multiplication by weight. Usually in standard neural network, you have to multiply by this weight for all of the
Mm-hmm.
inputs, right? But
Mm-hmm.
your sparse spike inputs are going to be quite sparse, so you can only look
Mm-hmm.
up the corresponding weights and just update that. So you don't have to do this matrix calculation, even in a standard hardware, a standard computing paradigm.
Mm-hmm.
Although there are like standard in real neuromorphic hardware, you have accelerators so that you can do all of these in parallel.
Like, as someone who doesn't know anything about this, my intuition is that also I noticed that since it only records change as opposed to recording everything, maybe there's computational advantages to that as well.
Yes, because your information is going to be very sparse, and you are
Yeah.
able to respond as shown in the pencil balancer example, right? You are
Yeah.
able to build a very low latency response system.
Yeah, it seems like the redundant information, which is the information that doesn't change, it's not recorded.
Precisely, yeah.
Also, going back to your MNIST example, you mentioned that your camera was doing a circadian rhythm, right? So if we were to change that rhythm up, would the system still perform the same, or would it like?
You want to change that with what?
Uh, I don't know. So it's a circadian
Yeah,
rhythm, right?
but yeah. So the saccade, that's a fixed saccade, right? But when you look into more resemblance to a standard human eye, it's more of a random walk, right? That would also do. I don't see any problem with that.
Okay.
It's just that a triangular saccade was used because you could replicate that on a robotic system and convert all of the 70,000 MNIST examples easily.
I see. So if we were to train it on on a certain rhythm and then test it on another, like how would the system
We
perform?
haven't tried that particular example, but we what we have tried is the first video, right? The gesture, a human performing different hand gestures. So what we were able to do is we were able to train on few of those gestures and translate pretty well to some of the unknown gestures where we just train the last leads, and that translates pretty well.
I see. All right, thank you.
Uh,
I think there's a question
Yeah.
in the chat.
and, yeah, there's a question in chat. Mahendra, do you want to question yourself? Do you want to ask questions yourself? Mahendra, are you there? Okay, his mic is not working. So he's asked, like, in the high level, like how the learning is happening. Like in the traditional setting, we learn weights using back propagation. So how the learning is happening.
Yeah, so you can do back propagation in spiking neural networks. So that's a very exploding area of research. One of the issues, since you have temporal components, so you have to do back propagation a long time as well to account for the temporal information. But back propagation is very much possible. There are different frameworks to do back propagation. Also, in addition, you can also back propagate only when your neuron is spiking. We call that event-based back propagation. So since your input is also very sparse, your back propagation signal is also going to be very sparse. That's also possible. Also, people use more neuroscience or biology-inspired algorithms like SKP or different modulated forms of it. You could say, think of them as more Hebbian learning.
And thank you, sir. Mahendra, does that answer your question?
Yeah, I think he should write his answer in the chat.
Yeah.
Yeah.
Yeah, thanks. Okay. So do you have more questions? Anyone?
I had a question. So from what I understood, the spiking neural network in a spiking neural network, we're kind of converting the continuous voltage signals into some sort of a discretized form, and we're then operating on the discrete signals, right?
Yep.
So is there research where we kind of make use of the continuous information itself, where we use the continuous values of the voltage and then do what we're doing with the spiking neural system?
Oh, yes, you could do that. The filter bank encoding technique that I showed, if you remember that, there were a bunch of filters. So you could directly process the signals as they come and then convert it into spikes. So that's one of the ways. So this also has very much inspiration from neuroscience, where you can think of them as the receptive fields in an eye. The receptive field will collect the photons, and as they go on, whenever you have enough information, enough photons collected at that place, then it will fire a spike. The reason why you want to do a spike is you don't want to spend much information in communicating between the two nodes of the system, and also that gives you a high noise redundancy as well.
Just one request. When you are asking question, please mention your name as well. That'll be helpful.
No, Shashank.
I have a question. My name is Kaushal. First of all, thank you for your wonderful overview. And what I know, if I understand correctly, what the spiking neural network was doing is it was accumulating some information in the past, and it was using that information to sort of cross a threshold and essentially elicit a response in other neurons, right?
Yep.
And in the MNIST example as well, the digit we had was static, but the camera was moving around the number, and it was converted into a sort of temporal information, right?
Yes.
So what I wanted to ask is, do spiking neural networks, can spiking neural networks work with data that is static, or do you always need to encode it to something?
No, so That encoding is because of the neuromorphic camera, but you can always directly encode standard MNIST. You can do CIFAR-10 or Caltech standard datasets as well. The thing is, when you want to do that, you have to design or you have to implement some form of encoding techniques as well. Does that answer your question?
Yeah, what is there any specific type of encoding that maybe I can look into?
Oh yeah, so as I said in the slides, I described a couple of encoding techniques using population of neurons or different filter banks or the threshold kind of encoding. The threshold kind of encoding is the reason why you want to have movements in the camera, because whenever you don't have intensity change, you don't get any activity, and that's not going to work, especially for some static images, right? But your real world system, things move around, things don't get static, so it's not actually a problem for real world. But when you are trying to do image classification, that's a problem. So that's why we resorted to spikes, the saccadic movements basically. But what I can do is in the reading links, there are a few encoding techniques along the way. Otherwise, you can just contact me and I can give you more information on that.
No, I see. Yeah, thank you.
Amanda has posted another question. In your view, until when we can see the acetylene is beating the DNN-based system, and in which field domain it is going to be more impactful?
Oh yes. Personally, I think that spiking neural networks or neuromorphic systems are not well suited for image classification kind of tasks. That's where standard deep learning has its power. Part of the reason is because images are going to be static, and in a real system, everything is going to move. So you want to look at more of the temporal information in terms of video or some audio signals. So all of the real world signals are going to be temporal. And if you think of yourself trying to recognize an object, you don't just look at the snapshot and try and classify. You get a continuous stream of inputs in your eyes, and you're trying to process that. And that's where I believe that spike neural networks have real advantages. We have seen certain systems where spiking neural networks, because of their temporal ability, are able to beat LSTM approaches as well. But that's still part of the research process.
Thank you, Mahendra.
So the keyword is your temporal information.
Yeah, one thing I would like to add is, if you are a climate activist, then you definitely should go for neuromorphic computing, right? You'll be saving tons of energy.
Okay, you could have counter arguments to that, but
Yeah, so
let's see.
I'd like to ask a quick question. So what I'm interested, being a machine learning engineer, what I'm interested is, I'm very comfortable with ANNs, and I'm very comfortable with, compression and quantization, so that I can have low memory footprint and less computational powers and things like that. So what I would like to know is, how much trade-off, like maybe you have some benchmark for the action recognitions and some typical deep learning tasks. So what is the current state of the art, or comparison with the current state of the art?
Okay, I can give you some numbers on common data sets that people have worked on. Like for MNIST, using spike neural network, we can easily get 99.5%. That's not a problem. Even on CIFAR-10 as well, we can get early 90%, 92, 93%. I believe that's where the standard deep learning technology is as well. Although with spiking neural networks, since you are considering time information, it's difficult to scale it to the networks of the size of ResNet. That's purely because of the resource limitation.
Mm-hmm. So it will take some time for,
Yes, but let me repeat that again. Spiking neural networks, image classification should not be the goal of spiking neural networks.
Yeah, exactly.
Think of more temporal activities.
Yeah.
So hello, so I'm Rajesh. So I have one question to you. So you mentioned that one of the advantage and objective of neuromorphic computation is energy efficient, like Rakesh mentioned. And you also showed us some of the list of the like devices that are being developed on that part. So do you have any like some sort of numbers on how efficient the current devices are? And so I'm wondering what is the main reason for for those devices to be such efficient than the current computation devices?
Oh yes, there have been lots of research on that. That's how the neuromorphic hardware field has proliferated in recent times. When you look at the studies, typical benchmarks, you get at least an order of magnitude, if not hundreds of times more energy efficiency using in neuromorphic computing. People have tried that in what is that called? What's I can't recall what do you call when Hey Google or something? What's that called?
Voice assistant?
So not voice assistant. It's called there's a different word for it. Anyway, those kind of systems, right? And people have tried on these keyword spotting tasks basically, and you get hundreds of times energy efficiency. That is not using a purely optimized neuromorphic hardware. The reason there are like few hardwares which are going to be even more energy efficient. The reason for that is you only compute whenever you have the spike events, right? And when you don't have spike events, your network doesn't have to do anything. Spikes are sparse, so you don't have to spend much energy for routing that information from one neuron to another. And the most important is you don't have to do this with matrix multiplication, because spikes are binary event. If a spike occurs, you just increase the weights. You don't have to do any form of multiplications. And that's a multiplication is a very energy consuming resource in an hardware, even in terms of area and in terms of energy as well.
Thank you.
I wonder how they do in modeling generative distributions, like VAEs or GANs. Like, has there been work in that regard?
Current systems you can simply scale them to that big of a system. So we don't have a real comparison. Yeah.
So what might be the most ideal use case for this type of network, in your opinion?
Well, it's edge-based computing, where you deploy a system, and let's say you deploy a system on the remote side, and it keeps on operating, let's say for 6 months, 1 year, a couple of years, and it will try and do on the edge computing, and it only communicate when needed, right? So those kind of systems are perfectly suited for neuromorphic computing.
Are there any famous companies or famous names that we know of that has been using spike neural network?
For applications?
Yes.
I don't think so.
It's still in research phase, right?
Yes,
So
it's a very new field. The neuromorphic hardware, there been efforts like not too long ago, a couple of years back, there were very few neuromorphic hardware.
Is it this question might be kind of random, but is it in any way related to the current research that Elon Musk is doing?
No.
Okay.
Actually, that video of the pencil balancing thing, it kind of looked like the rocket landing. I don't know. It was just struck me.
Yeah, that's I think quite a good comparison. I haven't thought about it.
Yeah.
So, yeah.
Because it needs to happen like real time, and it's like a balancing.
Yeah. So we are, I think, almost towards the end, right? So any more questions?
So, hi, I'm Chitiz. I had a question. So, we are basically mimicking the neurons firing from the brain. So, do you think the problems that actually happen in the neurons that translate over to the spiking neural networks as well. So what I'm trying to say is that the obstructions in the brains and everything that happens. So basically, we are trying to model that, and those those adversarial attacks kind of relate back to this things or not?
Okay, let me rephrase that. So what you're trying to ask is, can we do adversarial attack on spiking neural networks?
Yeah, basically, yes.
Uh, I don't have a concrete answer for that, but because you can train spiking neural networks with backpropagation, and adversarial attack is a problem of your data-driven way of training the system, right? But I'm definitely confident that you cannot, your one pixel attack kind of thing, you cannot do that in spiking neural networks. But there might be other adversarial attacks specific to spiking networks.
All right, thank you.
Does anyone have any more questions?
Yeah, I have a question. Uh, Hi, I'm Promise. So my question is that nowadays many, like basically ARM processor manufacturers, they are including some sort of AI chip that they claim to be more efficient. So how does that compare to neuromorphic computing in terms of power and like application wise?
Yes, as I said, neuromorphic hardware are orders of magnitude energy efficient.
So compared to those of mobile
The
phone AI chips, all those things are
dedicated,
there.
yeah, is AI chips. Yeah.
Thank you, Ramesh. Um, is there any question? Okay. So I just want to request everyone like to write few learnings from this session in the chat box. Just write whatever you learned. It can be write in points, like 1 or 2, 3 main learnings. Then we can set up like 2 minutes for that.
Or maybe we can share the feedback form with them, and
Yeah,
they
sure.
can just
Yeah,
put
we should be
in.
sharing that as well. So I just wanted to like see.
Oh yeah, there's
Yeah.
from issue.
Yeah. Thank you, Ishu, for being the first one. Culture.
So all the hardwares, the Intels that you are working on, so all these are in research phase, right? You can't get them in production in the market.
You cannot. Yeah.
Cannot, right? And what about the DVCs cameras?
TVS cameras, you can buy them.
Mm-hmm.
There are a couple of commercially available. Even Samsung also produces a couple of them.
Mm-hmm.
But there are some Swiss-based company like Innovation and subs that sell DVS cameras.
We've just received received learnings from 3 people: Ishu, Kaushal, and Rajant. What about the rest? Well, I can see more coming. I think this will be helpful for like in writing, like we can send this learnings to Sumit sir as well. So, and we'll send the feedback home as well,
Sure thing.
feedback results and responses as well.
I joined a little bit late, so I don't know if you already said this, but uh, what is your current field of research?
Mine?
Yes.
My work is predominantly on spiking neural network, deep spiking neural networks.
I mean, is there an application you're looking towards, or is it like more theoretical, or?
We do work on different demo applications. So there have been a couple of hardware development efforts, and I am looking at the algorithm sides of it.
Like Mahendra pointed out, I'm really curious about how the gradients are calculated, and how back propagation works on this, like because it's a little bit different.
There are a couple of unique challenges, but that would be a long discussion. I'd say, yeah. But one of my work, if you just Google Slayer PyTorch, you'll end up in a Git repository, and you'll find.
Sorry, can you spell that out, please?
I'll type that.
Yeah, thank you. Again, thank you for your time, by the way. This has been awesome.
So the Slayer PyTorch is a Git repository where you can use backpropagation to train spiking neural networks.
Nice name.
So it should be pretty much familiar to guys who use PyTorch.
Thank you. We'll check this out.
Mm-hmm. But yeah, there are a couple of unique things because of the temporal interaction that happens in spike. And also, since spikes are binary, then a simple way to explain it is in your backpropagation chain, you have to have derivative of your activation function, right?
Right.
And you cannot mathematically differentiate your threshold functions.
Right.
So there are a couple of technical challenges.
Yeah. That's why I'm so curious.
Yeah, the technical maybe like I'll quickly say that I'll not go into much details, but this threshold derivative, right? So people use this idea of surrogate gradient, where you actually use the threshold function in the forward pass, and in the backward gradient pass instead of you use a surrogate function that needs to satisfy certain requirements, but that you can use those as proxy for the derivatives.
That's so cool. You said it's temporal, so can you control the range of how much temporal data it takes?
Oh yes. So if you remember, so whenever a spike comes, there was a certain bump, right?
Right.
That lasted for a period of time. So that actually depends on your synaptic model as well as your neuron model. So you can have different time constants that will change the shape of this. It's called a postsynaptic response. So you can actually change shape of this PSP, and mathematically it's not a problem. Even in biology, you see different variations of this postsynaptic response, and you can actually change that. In addition, what you can also do is since sometimes the neurons can be very long in nature, and whenever a neuron spikes, it takes a while for it to get transmitted to a receiving neuron, right? So you call that axonal delays or synaptic delays, and you can actually use those delays as a form of some short-term memories, and that's how you get better at more recurrent kind of tasks. So basically, the delays even extend the PSP response over time.
Yeah, we are already like 40 minutes past our session time. So if you don't have any questions, maybe you'd like to conclude, or shall we? Or we have discussed everything and we can just sign
Yeah.
off.
Hopefully, this presentation it has generated interest for everyone on this new topic. I deliberately didn't try and go much into the details because it's going to be a new thing and to spend a lot of time delving into
Yeah.
the details. But I'll be happy to do further discussions on more further details as well. And thanks, Rakesh, for inviting me.
Yeah, thank you to Sumit and thank you Akriti ji and the training team. They have been super helpful for organizing this session. So I think yeah, we can sign off now. Thank you everyone.
Thank you everyone. We'll send you all the feedback form as well. So please fill in the form by I think this week, so that we can send it to him as well. The responses to him as well, Sumit sir as well. And Sumit sir, thank you so much for your time and this for our presentation. And
Yeah, no problem.
and
I
we
will
heard that,
email you the reading resources.
yeah, sure, that we'll send the resource materials to everyone, so that'll be helpful for all of you guys. And I heard that you're traveling to US next week, so have a safe flight as well.
Yep. Thank you.
Okay, thank you very much.
Thank you everyone. Have a great day ahead.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye.
Bye.